Good morning, guys. Today we're going to continue exploring quantitative variables or quantitative data with our next unit, which looks at comparing two quantitative variables. We call it bivariate data if you're comparing two variables. Well, two quantitative variables, we're going to try to look at how we can organize those and analyze those and look for associations, relationships. So similar to how we did when we looked at two categorical variables earlier on in the course, now we're going to look at two quantitative variables. So here's our setup for today. We're looking at the 2011 SEC football results. We have all of our teams, and we're looking at how many points they scored per game and how many wins per game. So the idea on two categorical variables is I have one variable that I'm interested in, a variable that I want to, or sorry, two quantitative variables. I want to have one variable I'm looking at, trying to figure out a way to predict, and then I need to introduce another variable to help me improve my ability to make that prediction. So if we're looking at these two variables here, points per game and wins, I think what I would like to predict is how many wins would a team get. So if I want to try to predict how many wins a team can get kind of going forward, I think using points per game as another piece of information to help me with that should be something very useful. So if I was a football coach, which I am, and I wanted to try to figure out how I can get my team to win more games, maybe I'm gonna look at, okay, do I need to improve my offense? Okay, would scoring more points help me win more games? Or is there no relationship there? Does that not actually help me in that sense? So that's what we're trying to set up here, is we're trying to identify, does one help me improve my ability to predict and maybe look for a causal relationship later on. So when we're working with two variables, just as we did with our categorical data, we have one of them is going to be explanatory, one of them is going to be a response. Now, the response variable is the variable that we're trying to predict. So just like we talked in this case, the number of wins is probably what we want to be able to predict. So this would be our response variable. All right, now our explanatory variable is going to be the variable that helps us predict. Okay? So this helps us predict the response. So if I know how many points per game a team scored, can I predict how many teams or how many games that they won, how many teams did they beat? So for us, the points per game would be our explanatory variable. Now you guys can think of this as in terms of independent, dependent variables. Wins is probably dependent on number of wins, things like that. But I don't want to get too much into that right now because that gets into something we're going to talk about a little bit later in this lecture. But later on we talk about when do I look at for an actual cause and effect relationship. That's coming up later in the course. Now, how do we graphically organize? Because anytime we get data, we want to then get it into a picture so we can start trying to look for some type of association or relationship. Well, the way we graphically organize a scatter plot, or sorry, two quantitative variables is with a scatter plot. That should make sense to us because quantitative data we do with one number line, so two quantitative variables we would do with two number lines. So two number lines is just a coordinate plane. Now, the scatter plot, you've worked with these before. It's just taking your explanatory and responses and then assigning them either an x value or x-axis or y-axis. So in this case, the independent variable, the points per game, the explanatory variable, would that be the x-axis or the y-axis? Well, as you remember from your algebra courses, if it's independent, we want to put that on the x. So our explanatory variable is going to be our x values. So down here on the x-axis, we put points per game for 2011 SEC football teams. Okay. So that's what we've got down here, the points per game. That means that our dependent variable, our response variable, is going to go on the y-axis. So we're going to put our number of wins. So number of wins for 2011 SEC football teams. So this is our scatter plot. Now, how did I get all of these dots on there? Well, if it's got an x-axis and a y-axis, it's really nothing more than writing these as ordered pairs. So let's take Alabama right here. My x value, my explanatory, was points per game, and my response was 12 wins. So that's really nothing more than the ordered pair, 34.8, 12. So to graph Alabama, I went over to 34.8, I went up to 12, and there was Alabama. And I did the same thing for Arkansas. 36.8, so about 37, with an 11 on the vertical axis. So 37 and 11, so there was Arkansas. So we just worked our way down the line, making each of these into ordered pairs, remembering that my explanatory needed to be my x, and then my response needed to be my y. So all you're doing is plotting this the same way you've plotted ordered pairs in your algebra courses for years. So we've now taken two lists of quantitative data and just combined it into one list of ordered pairs. So that's graphically how we will organize. This is the type of graph we use for two quantitative variables. So over on my scatter plot, I've got this individual in purple right here in the middle circled. So not the red and blue, but I want to just talk about this purple circled individual. All right, so just going back and reading the scatter plot, describe the individual. Describe the individual. So when I look at this, what do I know about this? Not looking at the table, just looking at this individual. What information can I gather from that about that individual from this their location on the graph? So I want you to pause here for a second, and I want you guys to tell me, what do we know about that circled individual based purely on the scatter plot? All right, and hopefully you got something like this. Yeah, so what you can see, the only two pieces of information that we gather is what they scored per game and how many wins they have. So based on their position on the graph, I can see that they scored about 25 points per game and they won 8 games. Now, just like any graph that we come across in statistics, not only do we want to graph it, we want to then describe what we see in that graph. That's the whole point of making a graph, is to take a large set of numbers and turn it into something that we can start to identify patterns with. So once we get it graphed, we then need to describe. So we have really 4 things we're going to talk about in the description of a scatter plot. So very similar to when we described our quantitative data before, whether that was a histogram, dot plot, stem plot, box plot, any of those where we talked about shape, outliers, center, and spread. We're going to have similar things that we're going to talk about here. We need to talk about the overall pattern. We're still going to identify outliers and things like that. So the first thing when I'm describing a scatter plot is I want to describe the strength of the relationship. Okay? The strength of the relationship. Is it a strong association or is it a weak association? So when I talk about an association being strong, I talk about it having a clear pattern. Okay? When I look at the graph, do I see some type of straight line or curve or shape, anything that I can see? Okay? Is it predictable? So if I had an idea of where one x value was, where an explanatory value was, could I predict where the y value should be for that, or where the response value should be? That's what I mean by predictable. That's what I mean by a clear pattern. So strong relationship, there's a clear pattern. Well, a weak relationship would have an unclear pattern. It would be unpredictable. Data would just be thrown all over the place. We'd have plots or points scattered all over the place, and you really can't predict anything based off of it. So you might have some really high values and really low values and in between values for one x value, for one response explanatory value. So that's what we're talking about for strong versus weak. Next thing I want to talk about is the type of association that we get, positive association or negative association. So this is the direction that we're looking at. So a positive association, if we're looking at it graphically, increases from left to right. That's pretty straightforward. Okay? So positive association on the graph increases from left to right. But a lot of times we don't get a graph starting out on questions that have to do with this, and they just give us an association, or they just show us the data, and maybe we want to just determine if there's going to be a positive or negative association. So what I like to think of association is, how are my high values matching my high explanatories? What are they predicting, and what are my low explanatories predicting? So for a graph to increase from left to right, that means it has to be down on the left, which means that it would have low explanatory values and low response values. So I think of that as a low x predicts a low y value. Right? That's going to be two small values, so the graph's going to be low on the left side. And then a high x value should predict a high y value. So even if I didn't see the graph, I could predict whether something's going to be positive, whether it's going to have a positive association, because I can just look at the data and see, are large explanatory values related to, or paired up with large response values, and are small explanatory values matched up with small response values. Well, a negative association goes the other way. Okay, so from left to right, the graph would decrease. So it decreases from left to right. Then it has kind of that inverted relationship. Okay, so if it's decreased, that means it's much higher on the left side, so my low explanatory values are paired up with high or large response values. So that's where a low x predicts a high y value, and then vice versa. A high x value produces or predicts a low y value. Now, when we come into class tomorrow, be thinking about some types of relationships that might have a positive association and a negative association, because I want to kind of talk about some of those. So I'll give you a quick example here. If I did study time versus test scores, a little bit of studying should produce a small test score, where a larger amount of studying should produce a larger test score. That would be should be a positive association. Negative association might be practice time and golf score. Right? The less you practice, the worse you are, so the higher your golf score would be. But the more you practice, the better you get, so the lower your golf score should be. So those are a couple of examples of positive and negative association. But we come in tomorrow, I want you guys to have some ideas on what some examples that we can come up with positive association and negative association. So we've talked about strength, we've talked about direction. Is it strong, is it weak, is it positive or negative? Now what's it actually shaped like? So that's going to be the form of the relationship. So there are a couple of options here. First one is linear. This is what you worked with most of the time. So if I have a linear relationship, the dots are going to look something like that, right? I could draw a straight line and it models it pretty well. Now, a curved relationship could look like anything. A curved relationship could look like a quadratic, something like that. Okay? It could look like an exponential, something like that. It could look like anything. It could look like a sine wave. Who knows what it is? Okay? Usually, if it's linear, it's a straight line. Curved, a lot of times we'll just say non-linear instead of specifying a specific type of curve for this course. And when you get into more advanced statistic courses, then we'll try to put specific types of curves on. And towards the end of this course, we'll start looking at different polynomial curves that we can use, or things like that, exponential curves. But for right now, we really can just say if it looks linear or if it looks non-linear. And then clusters. So I may have a data set that looks like this, and it looks like it's all over the place. It looks like I don't have anything at all. But what we actually may look at is I might be able to look a little further and see, okay, there's actually two linear clusters going on here. So maybe we were talking about the relationship between height and shoe size, something like that. So if we were doing height and shoe sizes and then we saw that the data looked a lot like this and this, maybe we could go back and look and say, oh, maybe this was all the males actually ended up over here and all the females over here. So maybe if you get clusters, it's good to point out because maybe there's kind of a secondary, maybe a categorical variable that's actually in play. So you could actually be looking at three variables in that relationship. So it's good to identify if your data is showing up in clusters, because that's some other analysis or further analysis we can put into it. Now that we've kind of identified the three main features of a scatter plot, or describing a scatter plot, I want you guys to describe the association between points per game and number of wins. So looking at this, let's describe the strength, the direction, the form of this relationship. And make sure that you're identifying what the relationship is between when you do this. I'm going to pause it for a second right here and give you guys a chance to describe that scatter plot. All right, hopefully you have an answer that looks like this. Yeah, so what we see here is I came up with a relatively strong positive linear association between points per game and number of wins. Relatively strong positive linear association between points per game and number of wins. This is the format that you want to describe a scatter plot with. So as we're looking through these, we see we have the strength, relatively strong, the direction, positive, the form, linear, and we've identified both our explanatory and response variables. You need to have all three, or I guess all four of those pieces in the description of a scatter plot. We need strength, direction, form, and context. I need to know what two variables that we are relating to describe that this scatter plot is describing. So this is the format. Anytime I'm asking you to describe the association between or describe a scatter plot, you need to describe the strength, the direction, the form, and the context. Notice for my strength, I didn't say just strong, I said relatively strong. That's where these are kind of nice because you can kind of qualify things like relatively strong, kind of strong, moderately strong, things like that. It doesn't have to be a perfect relationship, perfectly strengthened, perfectly straight line. We can say, okay, it's approximate. All right, last thing we'll look at is right here. Would either of this red dot or blue dot, so I've got the red dot and the blue dot here, would either of them be considered an outlier? So I want you to just pause right here, think about it. Would we consider one of them to be an outlier, and if so, which one? Or would we consider both of them outliers, or would we consider neither of them outliers? So I take a second, pause the video, and I want to see what you guys come up with on why or what each of those is, or just kind of think about what each of those are, whether or not they're an outlier. All right, now that you've kind of thought about it, an outlier, as we know from our description way back when we had the 1.5 IQR rule, things like that, well, it's not as exact when we're dealing with scatter plots. So we're not going to do a calculation on this. We're going to eyeball them. We're going to look and see, are they an outlier based on our definition of an outlier. Now, usually when people think of an outlier, they're thinking of something that's really, really far away from the rest of the data. So both of these are pretty far away from the rest of the data. However, they're not both outliers. And here's why they're not both outliers. Only one of them is actually an outlier. This red dot, even though it's far, far away from the data, it still follows the same pattern. So if we go back to our very original definition of an outlier as any value or any individual who deviates from the overall pattern. That's what makes something an outlier. An individual who deviates from the overall pattern. Well, what is our pattern? Our pattern was that it's a positive association. That means a high explanatory should correlate or correspond to a high Y value. Well, this team over here scored almost 60 points per game, and they're up here at 17 wins. So you have a high explanatory and a high response. So that still follows the overall pattern. Now, they are an extreme value. They're way on out there. They're very different from the rest of the group, but they're not an outlier per se. They don't deviate from the overall pattern. So the red dot is not an outlier. Because it follows the pattern of the data set. The blue dot, however, does not. We said we had a positive association. So high explanatories, high points per game should produce a high number of wins. Well, a low point per game average should produce a low number of wins. This team right here won 14 games, but only scored like 5 points a game. That's an insane defense. They were very different from the overall pattern. So in this case, the blue team would be an outlier. So they're an outlier because they don't follow the pattern. So this is what we're talking about when we have a scatter plot and we want to describe it. Strength, direction, form. Okay, so how predictable is it? What direction is it going? And what shape does it take on? And then are there any outliers? Are there any individuals who just aren't following the pattern of the rest of the data set? Okay, now a second ago I just used the word correlate. Okay, we said a high X value should correlate to a high Y value, a low X should correlate to a low Y value. Actually, I'll talk about correlation right now. Right, so you can see we have here what we're calling correlation coefficient, and it's actually the linear correlation coefficient. Okay, so it's talking about straight lines. So correlation is how closely two quantitative variables relate to each other. How predictable is my response based on my explanatory. So when we talk about correlation coefficient, or R, that's our symbol for correlation coefficient. That's our symbol for sample correlation coefficient. We'll talk much later about population correlation coefficient. So my R, I'm using what's going on in a sample to predict what's going on for other groups. So the idea behind correlation coefficient is that it's a measure of the strength and direction of a linear relationship. Strength and direction of something that we know to be linear. So just a minute ago, we looked at describing this relationship as relatively strong. Well, our correlation coefficient is going to put a measure on it. It's going to tell us how strong that is. Now, correlation coefficient is a number that's between 1 and -1. So we're going to talk about the blender formula that we throw all of our data into, and it chews it all up and spits out a number. All right, so when that happens, it's always going to produce a number between -1 and +1, and -1 and +1. So the two things that it can tell us is obviously the direction. If it's a negative number, it would have a negative association. If it produces a positive value, it produces a positive association. Now, the second part is the strength of the association. That's going to come from the actual number. So the sign tells us positive or negative association. The value, the absolute value of the number, the size of the correlation coefficient is going to tell us how strong something is. So if something is close to 0, then it has close to 0 correlation. There's not much correlation right there. All right, so it's a very weak relationship. If something's close to 1 or -1, if it's a negative association, but if it's close to 1 or -1, then it's going to be very strong. It's almost a 1-to-1 relationship where it's a perfectly straight line situation. So what we end up with is any correlation coefficient that's here in the middle, we would consider weak. So if it was like a negative 0.5 to a positive 0.5, those would be just weak. But anything that's out on the tails, anything that's closer to -1, closer to +1, we would consider those strong. Strong. Now, usually if you're in that negative 0.5 or 0.5 range, it's going to be kind of, technically it's stronger than it is weak. But usually if we're looking for a very clear, predictable pattern, you're wanting to see a 0.7 or higher, or -0.7 or lower type situation. But by definition, 0.5 is kind of the cutoff between, or the marker between being strong versus being weak. Now, how do we get this correlation coefficient that we're talking about? Two ways to do it. One, we can use the calculator. We're going to show that one. But the first one is the formula. The formula is just the definition. So if I look at my relationship or my formula here, 1 over n minus 1, so that's just saying divide by the number of individuals, number of ordered pairs you have, minus 1. And we know we usually do that when we're talking about predicting and sampling and things like that, because we want to weaken the estimate. Okay, so 1 over n minus 1 times the sum of x1 minus x bar over sx and y1 minus y bar over sy. Now this should look familiar to us, because we've been working with taking a value, subtracting its mean, and dividing by its standard deviation. That's nothing more than the z-score of x. And this is nothing more than the z-score of y. So when we talk about correlation coefficient, when I take a bunch of numbers, a bunch of values, like all of my values, and I add them up and divide by however many there are, that's an average. So this is nothing more than the average product of z-scores. So I'm going to take an ordered pair, I'm going to get the z-score for the x-coordinate, z-score for the y-coordinate, and multiply them together. That's it. Ordered pair, z-score for the x, z-score for the y, multiply together. Now I'll go grab the next ordered pair. Z-score for x, z-score for y, multiply them together, until I've got all 12 products from my SEC team. So once I have all those products right there, then I just divide by n minus 1. Okay? Divide by the 11 in this case. So it's the average product of z-scores for x, y pairs. This is how we determine the correlation. Okay, so if I have negative z-scores, right, so that's what we're going to get here, right? So if I've got negative association, that's because my x values were lower than the mean and my y values were greater than the mean, right? They're going in opposite directions. So what's going to happen is a negative and a positive is going to make a negative. So if I have all of these negatives being averaged together, it should produce a negative average product. Where if I have a positive association, that means when my x's are above the mean and my y's are above the mean, they're both positive. When my x's are below the mean and my y's are below the mean, they're both negative. So again, those products are all positive. So that's how the association shows up right there. Now, the closer they are to the mean on average, or to that prediction line that we're talking about, so the predictable x, the predictable y, and we'll get into the regression line in the next discussion. The closer they are to that, then the closer they are to that, then the more we're going to get those to average out closer to a 1. So that's how we calculate it. Average product of z-score for x, y pairs. We're not going to use that formula ever, okay? I want to go to the calculator because I don't want you guys sitting there crunching numbers all the time. I want you being able to interpret these numbers. So let's go to the calculator and I'll show you how we can throw our data in and get it to produce a correlation or R value for us. First thing we need to do is set up the calculator so that it can read correlation coefficient. We should only have to do this one time, and then the calculator will be good to do it every time until you like reset the memory or something like that. So what we're going to do is we're going to have to go into the catalog. So second 0, scroll down to the D's, and what we want to do is turn the diagnostic on. So diagnostic on, that's going to give us a couple of values one of them being the correlation coefficient. So just hit enter twice until it says done. Now you're good. All right, now your calculator is ready to enter the data. We're going to enter it the same place we entered our data when we were doing one of our stats and just any type of numerical analysis on the calculator. So we're going to go stat edit, but now we've got to key in two sets of data. Now just remember we established, or we're going to key in the L1 is the explanatory variable, L2 will be the response variable. So for us, we said points per game was our explanatory and response were the wins. So we're going to key our points per game into L1 and then our response into L2. So I've already keyed these in to stat edit. And you can see I put L1 were the points per game and L2 were the wins, making sure that I match up the Alabama points and wins together, Auburn points and wins together, and so on. So you can pause it right here for a second and key that data in, points in L1, wins in L2, but I'm going to kind of move on into how we can calculate. So after we've keyed in our data, we need to actually run our calculations. So in the stat calc menu, you're going to scroll down and we're trying to do a regression model. And you've worked with these before. Option 8 is the one we care about. LinReg A plus BX. So we're always going to pick option 8, LinReg A plus BX. And in the X list, obviously we're going to tell the X's were L1 and the Y list was L2 because we said our explanatory variable was our points per game, and then our response variable was our number of wins. So LinReg, just do a quick check. Did I put my X's in L1? Yes. My Y's in L2? Yes. And when we calculate, it'll spit out a bunch of different numbers. What we care about right now is the R, which we were looking at right there. R is that correlation coefficient. So the R for us is this 0.93586, blah, blah, blah. So we're really just going to round it to two decimal places. So our R is 0.94. Now, if we think back to the spectrum we just talked about a minute ago, how R runs from -1 to +1, we can see that it's positive. We can see that it's really, really close to 1. So those two things tell us everything we need to know about R. So what we know is that it's pretty strong, close to 1, positive, obviously positive. So there's pretty strong positive association between points per game and number of wins, assuming the relationship is linear. So that's the important part right there. R by itself doesn't tell us things are linear. R tells us if they're linear, this is how strong, this is the direction. But we need to see the graph to determine if something's linear. We've already looked at the graph, so we know that this R is useful to us. So that's how we can use the calculator to get correlation coefficient. Key your X's into L1, Y's into L2, and then stat calc option 8. And just read the R off of the calculator. So now that we have looked at how to calculate correlation and from the formula or from the calculator, again, I prefer the calculator. Let's talk about kind of some limitations on correlation, what it does, what it doesn't tell us. So things that we need to happen with correlation. Both variables must be quantitative. And that should make sense because if I'm calculating z-scores, you can't do a z-score for categorical information. So both variables must be quantitative. All right, correlation does not care which variable is explanatory and response. Well, that just goes back to the definition of correlation. It's an average product. So if you swapped your X and Y variables, you're still going to be working with an average of 1. And so z-scores of 1 times z-scores of the other. So if you flip the order, the product is still going to be the same. So that's why it doesn't care which variable is explanatory and response. So you can look at two inverse graphs and they'll have the exact same correlation. It does not change if the units of the variables are changed. So if I moved from, I was measuring something in, say, feet, and I changed it over to inches. Well, that should again make sense based on what standard deviation, or what a z-score does. Because if I converted from feet to inches, this is 12 times bigger, this is 12 times bigger, but my spread is also 12 times bigger. Guys, remember that from our transformations, the locations, and the spread change when we multiply. So a unit conversion changes the values, but it also changes the standard deviation by the same rate. So all those times 12s just canceled out, and you're still left with the exact same z-score, same relative position. So if you change units, you're not changing anything from a z-score standpoint, so you're not changing anything from a correlation coefficient standpoint. Okay? Correlation coefficient does not have any units, because remember, z-score doesn't have units. It's your number of standard deviations, whatever that happens to mean. Okay, so you're just averaging a bunch of numbers together, or product of numbers. So correlation coefficient doesn't have any units. It's just a number. It's not 0.94 wins. It's not 0.94 points per game. It's just 0.94. It's a number on the scale, -1 to +1. That tells us it's positive and it's strong. That's all it is. It's just a number. And the last and probably most important, correlation does not imply causation. Just because two things are happening at the same time. We're going to spend a lot of time talking about this, especially once we get into our experimental design and causation inferences. Just because two things are happening at the same time does not mean one caused the other to happen. Okay? Just because the teams that won more games happen to also score more points does not mean that they won because they scored more points. It's a prediction tool, but it's not a causation tool. Now, we may be able to do other things and come to conclusions that the points per game was causal, but we'd have to go through a lot more analysis, and we may even have to set up a controlled experiment, which would be very difficult because there are a lot of other variables that we're not looking at. So just because two things happen at the same time does not mean that one thing causes the other to happen. So if you learn nothing else from statistics, I want you to understand that right there, because that kind of runs through a lot of data analysis and statistical analysis from people that aren't really paying attention. They see two things happening at the same time, and they go ahead and apply motive or intent or causation from one to the other. So make sure you understand, because two things happen at the same time, they're correlated. One does not necessarily imply that one caused the other. All right, so that's it for how we compare two quantitative variables with scatter plots, and then look at the correlation between those two variables. So make sure you got all this. Calculator is really, really helpful. These steps right here are going to be very useful going forward when we start looking at linear regression models and things like that in our next lecture. So that's it, and I will see you in class tomorrow, guys.